Here we're asked to graph this kind of function, which is a rational function. And that's what we are going to start with. So this is a rational function. And we were asked to graph it and go through all the steps that we know: first derivative, second derivative, concavity, inflection points, max, min, everything. And we did this last time already. And we found all the points, except I ran out of time. I was supposed to determine these values. So I'm going to plug them in right now. So I'm going to share my screen and just plug in y equals, where are you guys? Okay, I see it. I see you. Okay. So in y equals, I'm going to plug in this function. Clear if you have anything else. X at the top. And divide by, in parentheses, x squared plus 1. Close the parenthesis. And simply I go back and plug in the square root of a negative square root of 3 and positive square root of 3. I know that this function is odd. So if one is negative 5, the other one will be positive 5. How do I know that? I'll show you in a minute. So negative the square root of 3. And I guarantee you that if this is positive, the other one will be identical negative. So if this is negative, the other one will be identical positive. You don't have to do it again, but let's do it just to convince ourselves it's the same number but positive. So I'm going to copy, just for now, negative 0.4 for the first one and 0.4 for the other one. Okay, I'm going to stop sharing. Okay, so now I have really everything. We went through, let me refresh your memory. We determined the x and y intercepts. We determined the limits using L'Hopital's rule. We found the first derivative and the critical numbers. We found the second derivative, and where the second derivative is 0 or undefined. It was never 0 because x squared plus 1 is never 0. So we got all this. And we put them back in the table. We summarized all the information in the table. This is crucial to remember. These were horizontal asymptotes, so it's just one horizontal asymptote. And it turns out that this is an inflection point, IP. How do I know? The second derivative is 0 or undefined, but here it's 0. And it changes sign. 0, 0 is another IP because the second derivative is 0 or undefined, but it's 0 in this case, and it changes sign. The square root of 3.4 is another IP, inflection point, because the second derivative is 0 and it changes sign. Now all the information is summarized. I don't care for anything else. And now I'm just going to graph the function. I don't want to look anywhere else. It would be a waste of time. And my table tells me what to do. Stop me anytime for questions, anything. Anything, if you want to say something, please do. First, I should draw the horizontal asymptote. There is no need, is y equals 0. That would be an overkill. So y equals 0 is the horizontal asymptote. Now I will plot the points I have. And I have 0, 0. I have negative 1, negative 1/2. I have 1, 1/2. I have the square root of 3, which is roughly 1.7. So 1.7 and 0.4. Well, I'm going to say right here. And negative the square root of 3. And negative 0.4. And that's about it. And now, ready for the graph. From approaching the horizontal asymptote, opening down, to this first point of inflection. From approaching the horizontal asymptote, opening down, till the first point, negative the square root of 3, negative 0.4. Where it changes concavity, it continues to decrease, opening upward towards this point that is the relative minimum. It continues to open up. It's increasing towards the origin that is also a point of inflection. I put an arrow here. With my marker, it looks like it touches the horizontal asymptote. It does not. I'm sorry, my marker is kind of thick for you to see, so it does not touch. Okay, I don't have to look at the rest because I know it's an odd function. How do I know? Because the function, if I replace x by negative x, I will obtain the opposite of f of x. Assuming I don't notice that, we'll continue. It changes concavity, opening downward, going towards the relative max, opening upward, opening downward, approaching the maximum. It's still opening down till the point of inflection, where it changes concavity, opening up and approaching the horizontal asymptote. So this is the function, rational function x squared plus 1. And the calculator will not be able to give us these points. We are able to determine them using calculus. The calculator will not give us the points of inflection. It will give us this, but it will not give us these 2 points of inflection. And now we know everything about the rational function, and everything was summarized in here. I only copied it here. Any questions on this? Any questions for me? So I'm going to post these. Gonna put the date here and say from last time, these 2 pages. So I guess I'm going to change this into 1 and 2 and move on to 3. Any questions from me? Anyone? Did you have any difficulties with the homework? Do you want to ask anything? Anyone? Okay, so
I have one question.
yes.
Okay, so when we ask to find like just give me 1 second. When we ask to find like the critical number.
Yes,
so
we find the derivative. We find the derivative and we set it equal to 0. Or if it's undefined, we find the x values where it's undefined.
Okay. My question is, do we just find the first derivative, or we find both the first and the second?
For critical numbers have nothing to do with the second derivative.
Okay.
So
it's just the first one.
So one more time, that's why I created this table for you in anticipation to this question. The first derivative has to do with these 2 only, the second derivative with these 2 only. So this has nothing to do with this has nothing to do with this. Is that okay?
Yeah, that's okay.
Perfect. That's why I created that table, so there is no confusion, because it may be confusing. Okay, very good. So we're going to look at the rational functions, and you could say, but what about this one? What was this all about? True. Now we're going to go into more detail. So rational functions are of different types. I like to call type 1 a rational function like this one. For example, f of x, x plus 1 over 3x minus 2. Why? Because it has the same degree, degree n over degree n. I like to call that type 1. Type 2 is a function, a rational function with a higher degree in the denominator. For example, x minus 1 over x squared minus 4. So I will say degree n at the top, but here degree greater than n. We also have something called type 3. Type 3 is very specific also. It's something like, let's say, x cubed minus 1 over x squared plus 1. Specifically, if this is degree n, this is degree n plus 1, exactly n plus 1. If this is 2, this is 3. If this is 10, this is 11. If this is 7, this is 8. And type whatever. Anything else that does not fit these categories. If it's the same degree of a same degree, I will call it type 1. If it's higher degree in the denominator, type 2. If it's higher at the top exactly by 1 unit, is type 3, and everything else is whatever. It can be degree 5 over degree 2. I don't have a name for that, and we're not really equipped to look into that very much. Okay, so what is different here? All these functions, I'm going to disregard this because I don't even know anything else. All these functions can have vertical asymptotes. What's a vertical asymptote? Oh, we graphed something like this. Or we looked at a domain for something like a function like this. If this is x equals 2, I'll say x equals 2 is a vertical asymptote. What does it mean? The function approaches infinity to the left of it, or negative infinity to the right of it, or both sides this way, or both sides this way, or the other way. This one up here and this one down here. This is a vertical asymptote. The function does not exist at this point, period. Okay, now these two, the first two, may have or can have horizontal asymptotes. This one can have a vertical but not horizontal. This one is the only one that has a slant asymptote. What's a slant asymptote? What's a horizontal asymptote? This is a horizontal asymptote. So the function gets closer and closer, closer and closer to infinity. When x approaches infinity, the function approaches 0. When x approaches negative infinity, the function approaches 0. We had this a minute ago. As x goes to infinity, the function values approach 0, and the other side as well. Okay, so we know what a vertical asymptote looks like. We know how a horizontal asymptote looks like, but what is this? Okay, we're going to look at situations in which a function, let's say, by the way, it cannot have horizontal and slant at the same time. If it has horizontal, it cannot have slant. If it has slant, it cannot have horizontal. So it's one or the other. I'm going to write a note here. Only type 3 has slant asymptote, but not horizontal. Okay? It cannot have both. So how will a slant asymptote look like? Something like this. Now let's say here's the function. Vertical asymptote, slant asymptote. So this section is all about these rational functions, determining their vertical asymptote for these two, horizontal for this one, slant, and graph. Exactly what we did here, but a little more different types of problems, and I let you choose, of course. We are on page 231. That's all we are going to talk about in 2.3. That's it. Okay, so let me start with one, and then you will choose the next one. Okay. I'm choosing 48, and you'll see why. on page 231. So this is f of x equals x plus 1 divided by x squared minus 2x minus 3. First, I would like to identify the type. Can anyone tell us which type is this?
Type 1.
Is it type 3 since it's one more than the...
So, what is the degree of the top?
1.
Thank you. What is the degree of the denominator?
2.
Okay. Which one has that situation?
Type 2.
Exactly. Very good. So this is type 2. Good. Higher degree in the denominator than the numerator. Next step, I have to start with the domain. Can anyone tell us what I need to write in order to find the domain of this function? Or what I need to do?
Solve for 0 for the denominator?
Okay. Absolutely. That's correct. Excellent. But maybe I want to factor it already.